So today's last speaker is Charlotte Pretzsch from the King's College in London, and she will present her talk on low field versus 3T high field MRI, vertex-level measures of neuroanatomy in a pediatric LMIC cohort.
Thanks for being here and for holding out that long. I realize I'm the only thing between you and lunch, so thank you for being here. I was already introduced. My name is Charlotte. I'm a research fellow at the IPPN, and I'm here to talk to you about my work on low-field imaging. I have no disclosures, but a lot of acknowledgements that you can also find in the paper that's just been published. So conventional neuroimaging, or 1.5 to 3 Tesla imaging normally, has obviously been immensely useful for research and clinical practice, and that's why most of us are here at the moment. But it is also very expensive and is very heavy and immobile. And because of that, it's not really accessible for a lot of people around the globe. And in response to that, there's now been a development of newer low-field imaging technologies that are usually below 0.1 Tesla. They are cheaper and they are more portable. And because of that, they're a lot more accessible, especially in low-resource settings, including in low- and middle-income countries. And previous studies have already shown that low-field imaging is feasible, including in children. It's reliable, also in adults, and it provides valid measures of the neuroanatomy of regions and tissues and the whole brain. But what we don't know yet is if it can provide accurate measures at the vertex level. And there's a lot of reasons why we're interested in that. And one of the reasons is that obviously most of the high resolution, sort of high field imaging is being conducted at that resolution, and would be really useful to be able to compare low field imaging findings to that, to probe, for example, the mechanisms underpinning different conditions. And also it would be very helpful to have this high spatial resolution data in order to integrate low field imaging with other related modalities, like for example, imaging transcriptomics. So to answer this research question, we studied paired data from children that were scanned in South Africa, in Cape Town and Stellenbosch, as part of the AIMS2 trials and the Safe Passage study. And we collected high field data as a sort of reference, and then low field data. And we processed the high field data using pretty standard procedures, and then the low field data. I don't know if anyone here has worked with low field data, but one of the biggest problems with that is the low signal to noise ratio. And there's a couple of things you can do to address that. And one of them is to use AI tools like Synthesar to work on the data. You can also, if you want, combine different imaging sequences or contrasts or whatever you have into one to try and increase the resolution of your data. So we tried some of those. You can see that on the right. I realize it's a little blurry. And then we put the data through FreeSurfer, FastSurfer, or Reconal Clinical, which is a FreeSurfer pipeline that's been adjusted for clinical images. And for each of these, I've got a pointer. No, I don't have a pointer. Now I have a pointer. So for each of these analytic strategies, we computed cortical volume, surface area, and cortical thickness. And then in the first instance, we just compared the high field data to each of the low field strategies. And then we, in the second step, compared the comparisons. So there's a lot of results, and I don't expect you to look at all of them. But just to give you a bit of an idea, I want to show you the cortical volume results. So each row corresponds to one of the metrics we use to compare the high field and the low field data. And each of the columns corresponds to one of the high field, low field comparisons. And red is good and blue is bad, and green is sort of in the middle. And you can see there's a lot of red, and there's also some green going on. So there's a lot of regions where the association between high field and low field data is actually pretty good. And then there's also some regions where it's not so good, where it's quite weak. You can probably see, just with a quick look, that there's some differences across the different columns. I'll go into those in a bit. The volume results are quite similar to the surface area results. The cortical thickness results, however, are quite different. Overall, it's a lot of green, meaning the association between high field and low field data for cortical thickness is quite poor. To sort of compare the comparisons, like I said earlier, the first thing we did was we literally just at each vertex in the brain looked at which strategy is the best strategy here, and we dyed that, so it's very high tech. But then we downsampled that a little bit just so you can understand it better with the naked eye. And what you can see is that there's a lot of heterogeneity going on. There's not really any regions where any strategies perform like wildly better than others across the brain. You can also see this here in the plot on the right. So these are the global averages across all the vertices. So basically across the board, cortical thickness, like I already showed you on the previous slides, does really poorly. And then volume and area are quite similar, usually between 0.3 and 0.5. This is just the Pearson correlation here. But there's not really any analytic strategy that does globally like way better or way worse than all the other ones. And to make that a bit more sort of practical for you guys, we also computed the percentage across the cortical surface where each strategy performed the best. So the point of this table is, you can look at the areas that I've shaded in blue. Oop, how do I go? There we go. So basically, the numbers, for example, if you look in the first column, looking at the MRI Riconal clinical data, so that's the 3 orientations combined into one and then processed using Riconal clinical on 26% of the cortical surface. If you're interested in volume, that strategy did the best. And if you look at that across the columns, there's probably a few rows or a few analytic strategies that overall did the best if you're just interested in coverage. Because that's a lot of results, we've developed an app for that as well. You can download that using the link. The paper for this was actually just published 2 weeks ago or so. You can also read that with the link down there. But essentially, you can use the app and you can just click through the results. If you like, you can, for example, download a mask from there. So if you have low field image results yourself, you can create a mask based on, for example, the regions that are particularly reliable and download that and then threshold your own results if you want. Or if you're interested in a particular brain region, you can also go into the app and then check which strategy is the best one to analyze that region. So to get back to the original question, can we use low field imaging to get high reliable, sort of high spatial resolution measures? Yes, we can, but it depends on where you're looking. So in some of the vertices, we had near perfect agreement, and then other vertices, not so much. Overall, I would probably say that the frontal regions do a little bit better than, say, for example, the occipital cortex. And that might be the position in the scanner of those regions. It might be the sort of inherent neuroanatomy of those regions. It also depends on what you're looking at. So cortical volume and surface area, like I said, they do quite well. Cortical thickness, not so much. And previous studies have also shown that already. And then it depends on what you've got available. So if you're planning to use low field imaging at some point, you need to think about how much time have you got to scan people, because the scans take a while. How much computing power have you got to analyze the data and so forth. And that might not be an issue for you if you're in a high resource setting. You might not mind at all. But if you are in a low resource setting, you probably have to think very carefully about how much data you want and how much computing power you've got to process all of it, to make the most of it. So maybe of interest here is, because obviously this was just a pilot study, so we need to expand this as usual and validate it in larger groups and so forth. But the reason why we did all of this work was because we're now starting to analyze the Bono cohort. And I don't know if you heard about it, but it's a very cool data set collected across South Africa with about 1,000 children and about 500 mums. And we're using this data. All of these people have been scanned, and we're using that data to analyze how early life adversity might affect later outcomes. So the work that we did here was pilot work to kind of inform the analytic strategy for that data set. So yeah, I'd like to thank everyone. It's been quite an international project, and it's been really fun. And thanks to the participants, and thanks to you all for listening and for still being here.
Thank you. We have time for questions. Do you want to come to the microphone? Yeah. Also, you can put something in the chat thing.
All right, thank you. So wonderful data. I didn't catch how old the children were because they might be moving or their gray-white contrast may not be as sharp as adults. And do you think if you do this in adults, do you get better reliability?
Yes, I think I would. So the kids were between 12 and 15 years old. I didn't show that. We looked at the effects of age as well. They were very minimal. But generally, if we look at adults, quality is a lot better. But a lot of so Unity, for example, which is probably the worldwide largest consortium at the moment using hyperfine imaging in children across the global south. And a lot of this work is done in children, so it's really important to validate these methods in children because that's where they're currently being used probably the most. Yeah. If you have any more questions, you can also email me, and I have a poster at poster 1934, which is just the flip of your poster, which is 43. Yeah.
Okay, then I think we close the session just in time for lunch, and thank all our speakers again.